Welcome to What That Means with Camille, where we take the confusion out of tech jargon and encourage more meaningful conversation about cybersecurity. Here is your host, Camille Morehart.
Hi, and welcome to today's episode of What That Means, part of Cybersecurity Inside podcast. I've got Lee Phillips with me to talk about 5G and 6G technology. Lee Phillips is a director and senior wireless strategist at Intel, and he advises Intel's global supply chain on wireless technologies. He pretty much knows everything about radio frequency. I've worked with him in the past, and I'm really delighted to have him on. Welcome, Lee.
Hi, thank you. Thank you for having me.
5G and 6G, kind of a big topic, and I'm wondering if you can just start us off by defining what is 5G.
So 5G is fifth generation wireless. So we started out with 1G or amps back in the early 90s. 1G was analog. Analog is when you had these giant batteries and these giant phones, because analog uses so much current, you had to have a giant battery and a giant form factor of your device, end device, in order to support that protocol. Then we got to the first digitized communications in this space was 2G. So in 2G, that was a 200 kilohertz bandwidth, right? So now you have the digitized protocol using less battery, less energy, but and you can do phase shift keying between different channels such that you can actually communicate in a digitized way. But that was very limited. It's only voice calls and some SMS or some text calls. Very, very limited. Then we moved to 3G. 3G has on average, a 5 megahertz bandwidth. Now you have 20x the bandwidth. Now you can start doing things, just calls, SMS, and now starting to do some data analytics or data translation, not just voice, but data now, right? So that was limited as well, because we had just a through pipe that was 5 megahertz wide in bandwidth. Then we move into 4G. 4G was a different beast altogether. Now it has...
This gave us like video calls and whatnot, right?
Exactly.
And streaming and okay.
Exactly. Now 4G or LTE has 1.4, 3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, and now up to 20 megahertz bandwidth. So now you can have a giant pipe of data, right, that can actually translate to things like you said, video calls and so forth. But it was also still limited in terms of usages, right? You can't take a 4G phone or 4G network into an automated factory because of latency issues. You couldn't take a 4G network and build out a massive machine-type communications network of millions of devices because of the protocol itself. It was inefficient in terms of how to translate that data into multiple end usages without a very, very expensive infrastructure. And now comes 5G. 5G is then broken down into, again, it takes that 4G anchor, 1.4 to 20 megahertz bandwidth. So for massive machine-type communications, it actually takes a different protocol, instantiates it such that you can have up to 1 million devices connected to a network. Then it also takes the latency from 1 to 4 seconds of latency in some usages down to around 10 milliseconds, such that now you have more real-time human-machine interface connections. So again, 5G is taking the best of 4G, and then adding the ultra-reliable networks and adding the ultra-connected sensor networks. Yes.
And so what is massive machine type communication?
So for LTE, you can connect up to 2,000 devices per base station. So a base station is a center of a cell, hence cell communications, cellular communications. So now for 5G, you now have up to 1 million devices connected to a single base station or single communications node. So again, the protocol is shaped in a way that you can connect multiple devices across. If you want to, for instance, if you want to go into a college campus, or if you want to go to a connected office space, you can now have multiple devices connected to the same 5G protocol for cellular, in this case 5G, and then offset some of the Wi-Fi traffic onto a cellular network.
So this is done primarily because we have so many more devices connecting, be they additional cell phones, but also like Internet of Things type of devices that we didn't have as many of before. So we just have to basically make room for more nodes connecting.
Now, this is correct. So now we have we walk around with our devices on person, right? We drive around with our devices in our garage and outside in the ecosystem. Our small, shorter range technologies like Wi-Fi and Bluetooth are up to maybe 50 meters on a great day. 50 meters, no line of sight. 5G can go up to 50 kilometers. So now we can have both on-premise and off-premise connectivity. You can be on a video call talking to your mother. You have your kids in the car. You start the conversation. Everyone's talking. You drive away from the home. Take your kids to the doctor, to the mall. And your call continues with the same video quality as at home, as in your car at the doctor's office. Even though
what about when you go in the parking garage after the appointment? Does it drop?
By the way, that depends. So in 2G, so now we'll start back in theory. So 2G, it was at 800 megahertz and 900 megahertz. So the lower the frequency, the better the penetration through things like garages and so forth. So 2G had 4 bands, right? 800, 900, 1800, 1900, right? So low band and high band. You go to 3G, you had 10 bands. You go to 4G, now you have, I think, up to 44 bands is the last I've counted. That we have, again, the same 2G bands, the same 3G bands, and a multitude of low, mid, and high to use the spectrum more effectively in order to reach whatever usage that you may need. But at the same time, when you use the lower channels or the lower frequency bands, it uses more energy. Think about if you have a teenage son and you hear him playing his music in the garage or in the parking area. You don't hear people talking the higher frequency, but you hear the bass, the lower frequency. In order to generate that lower frequency, it takes more energy to generate those longer wavelength sounds. So AM radio is in a very low frequency range, such that when you travel in your car, you rarely lose connection to an AM radio, even sometimes in tunnels, because it's a lower frequency range, right? Now, and AM is a big chunk of frequency. So a lot of government usages used to use AM radio because it had that ultra connectivity, pun intended. Now, more specifically towards cellular. Cellular starts around 450 megahertz, right? It's only used in a variety of ways, a smaller variety of ways than traditional cellular that starts at 698 megahertz. So the 698 megahertz is that low band. I was talking about 2G, right? 800, 900 megahertz. So then it expands to 1800, 1900 megahertz for 2G. I said 3G came on and it had the same 2G bands, but added more mid band and high band. So when 3G came on, it added bands up to 2.4 gigahertz, right? At 2.4 gigahertz is the same frequency band for Bluetooth and Wi-Fi. So now we have cellular, Bluetooth, and Wi-Fi in the same frequency band. Therefore, we need to have radio strategies in order to reject. If I'm talking on my cell phone, I'm going to reject the Wi-Fi signals. I'm going to reject the Bluetooth signals. And by the way, GPS also exists there. So I'm going to reject the GPS signals. Or if I'm using my GPS as a receiver, I'm going to reject, if I'm making a phone call, I'm going to reject my cell frequencies such that my GPS can actually be accurate and work seamlessly with my usage model, right? So now we're starting to have multiple radio frequencies and multiple radio usages in the same frequency bands. So now this is why a lot of these things, more usages, more radio technologies come on board. This is why our devices become more complex, because we want to actually use our device in a way that doesn't interfere with our environment. And by the way, we want to use the other usages for our other radios so that it doesn't interfere with our cellular.
So 2 questions. Why are so many technologies in the same band? Why don't they use different bands? Is that band easier to do something with, or the information goes better through that band?
Great question. So the government, in the U.S., the FCC governs what radio frequency bands are used for what usage. Maritime, satellite, geospatial, whatever, right? You could have a Fitbit on your bicycle. It all falls into these usages. So the FCC governs how what radio bands are allocated to what usage or what radio technology. So now, because we have multiple usages as defined by the government entity, our regulatory body, FCC, we have to then develop technologies that can actually be used as a singular device and be used in a multi-device environment. It's called coexistence.
Right, so that you don't interfere, like your Fitbit's not interfering with maritime communication or something like that.
Correct. By the way, maritime communication is a very, very, very high power thing. Like multiple kilowatts, and your Fitbit is like a milliwatt type of thing. But if you can do this, if you get close to a radio without if you have an older cell phone, right, one of these old Nokia phones, and you key this old Nokia phone next to a radio, an older radio, there will be interference. So over time, all the radio technologies became more mature, such that based on usages, because they define a radio, right? Here's the next generation cell phone, and it works good in a lab, but you have to take it out and do field trials to make sure that it's going to work good in usages around other interferers. They call them interferers in this space.
So is it possible to run out of bandwidth?
So we have to talk about what is bandwidth and how is consumed, right? So what is bandwidth? So this bandwidth is the amount of data that can be translated through a communications pipe, either wired or wireless. In this case, we're talking wireless. The more data I pump through a single channel, right, the more other things can't use that channel. And therefore, because we have very complex environments, we can't have one pipe for all traffic in the same frequency band. So right now on your cell phone, you have cellular and Wi-Fi Bluetooth in the same phone. And you have GPS in the same phone, all using 2.4 gigahertz. So what the Wi-Fi guys did is, guys, this thing is getting congested. I'm not getting enough Wi-Fi through. So I'm going to create a 5 gigahertz Wi-Fi band. Right? Now we have 2.4 and 5 gigahertz. The GPS guys are like, guys, if I'm on GPS, I have 9 channels in GPS. I can't use channels 1 through 5 because that is the low band of cellular. I'm the high band of cellular. I want to use the channels 6 through 15 or whatever for GPS because it's less congested. Now I can receive my GPS from whatever satellite and have very good fidelity and signal integrity. Like right now, I'm on a Wi-Fi call, right? And we're having a data conversation. At the same time, my computer is downstreaming emails, and we have great video quality and great sound quality, even though we're about, I would say, 1,200 miles away from each other. But all these things are pretty amazing. So all these things are interplay that we take for granted these days, but there's a significant amount of technology evolution in order for us to have this seemingly seamless communications environment.
I was wondering if the millimeter wave was the same thing as the airport alternative to the X-ray, the millimeter wave technology.
There are multiple usages for these wireless technologies. So now, actually, the airports use microwave to scan through different media in order to get Doppler feedback on their sensor screen such that you can see whatever dense material versus non-dense material can show up as a potential threat. Right? But it's microwave technologies. So again, all these wave technologies, it's a different frequency band in millimeter wave, but it's the same concept. So in airports today, these guys have all kinds of technologies. But I would say that the airports are kind of leading edge in terms of how they can actually translate media, right? Use a bunch of radio technologies in a coordinated fashion such that they can actually extract information and intelligence from the environment as much as possible. And then also allow people to have freedom of using their own devices.
Right, occurring at simultaneously. So it's interesting. All of the different pieces of information you can derive from wireless technologies. I had Lema Nachman on, a fellow at Intel, and she was talking about intelligent systems, and she did talk about some of her research in Wi-Fi and how looking at the interference of the signal can actually detect, like whether there's a person breathing. So very, very interesting kinds of stuff.
Yes, I will tell you, there's some research in the industry for automobiles, right? So they actually place a sensor network above your steering wheel in the console of your dashboard. So the sensors actually send out beams that actually take the moisture content from your forehead, and then they can actually extrapolate if you've had one sip of wine or many sips of wine. Therefore, your car may not start, or may send a beam back to whomever is monitoring these things about your condition. So there are many, many, many applications in this space. The 5G is opening up new doors. Well, 6G is a coming protocol that's going to allow even more usages. 6G is still in the early ratification phase. It's supposed to be ratified or planned to be ratified around 2026.
When do we see broad adoption of 5G? When are essentially most things using it?
Right. So every 5-6 years, these technologies evolve from one protocol to the next. So now we have, again, as I said, back in 2013, LTE came alive in a very real way. But LTE was defined by 3GPP, the radio standard, in 2006. It took that many years for it to come off. So 5G defined in 2019 as a 3GPP protocol, and now it's 2022 today. It's going to be a couple of years before it starts to really ramp in a real way. But because 5G, 2G and 3G are being sunset, right? So now the LTE anchor is there, and 5G uses that LTE anchor. So now we can market 5G devices using an LTE anchor. So you'll see a lot of marketing on 5G devices, but they're really using an LTE infrastructure. True 5G is standalone, right? So that 5G standalone will likely, the market analysis is all over the place because it's regional. Korea is in some cases leading. China has the most 5G base stations built out in the world. In some cases leading. AT&T, Verizon, and so forth. North America has the latest devices, right? But the infrastructure is lagging in China, so it depends. It's regional. But around 2023, 2024, we're expecting to see a giant boom. But before then,
it's a whole new build out of infrastructure to have true 5G, as you're saying.
Standalone
new cell towers,
correct?
Or at least new additions onto those cell towers.
This is correct. This is correct.
Well, you said 6G is going to have something new in it. What is that? Or new usages? What is the main new usage 6G is going to give us?
A lot of terrestrial and extraterrestrial communications, right? Are in mindset. A lot of mobility applications are in mindset. You
talking satellite or alien, my friend, when you say extraterrestrial?
Exactly. Satellite, right? Right. So extraterrestrial. Then
I had a moment of extreme excitement there until I realized you might mean satellite.
Well, they do have civilian entertainment shuttles now, but again, I think my paycheck can't support it. But then we have mobile usages and a variety of other usages. And then we talked about a few things, right? How can we use waves to extract information in nondescript ways, right? All these things are. How do we actually create as much data pipe as possible with as much sensor in our environment as possible to create as much intelligence as possible, real time, right? So that becomes both reactive and predictive. So a lot of these things like the meta that Facebook is changing to, a lot of the things that you see, drones and artificial intelligence being used, so autonomous things being implemented and so forth. All these things still have a latency aspect, even with 5G. All these things still have limitations in passing through different media. All these things are limitations. Although they are translation light years ahead, pun intended, above where we came from. Mm-hmm. Yeah, so the world is our oyster, and it's going to be very exciting. Yeah.
Okay, so one more thing,
Sure.
One more question. We're putting out filling the airwaves with transmissions in all different frequencies, getting more and more and more subdivided within that. Is there any concern or is there any look at like biological implications to transmitting so much information all over the place and continuing to fill that in?
Yes. So there are actually regulatory bodies in the government that study things like SAR, the surface absorption rate, right? So how much, when your phone transmits this 2.4 gigahertz or 5 gigahertz frequency or your Wi-Fi, and your body accepts this, it passes into your body, right, or through your body, what happens to your body? So there are giant regulatory bodies around the world looking at this. I do think bodies that define new radio usages, radio technologies, they must take into account how it impacts the human body. Not just human body, animals as well. So a lot of farms around the Midwest and the big farm areas have cell towers on them because that's cheap land and they generally flat. They can reach a large population or a large area of population in that space. Right? At the same time, cows and things that we consume, vegetables that we consume, are in the same space. So there's a lot of study here.
Do you wear your cell phone on your person?
Not all the time, no. But usually I'm riding a horse somewhere or this kind of thing, so I don't want to get it broken. But I do have a healthy separation between this ubiquitous technology environment and my person. I think everyone should do that. We can't submerge it. We are humans, not an autonomous bot, right? So we need to have a healthy connection between our environment and ourselves.
Lee, it's been so good to catch up with you today and listen to, you're such a wizard when it comes to understanding and articulating really complicated technology. Thank you so much for being on the show.
Camille, thank you for having me. And I really do support what you're doing not just for Intel, our mutual company, but for our world. We need to talk about these tough topics. So thank you for your mission in this space. Thank you.
Never miss an episode of What That Means with Camille by following us here on YouTube. You can also find episodes wherever you get your podcasts.
The views and opinions expressed are those of the guests and author and do not necessarily reflect the official policy or position of Intel Corporation.